Disappointed I'm not there because I really do like talking about electrolytic cells. So we will have more than enough time Friday and Monday and beginning of next week to make sure that we see these, we do these, and we actually get our hands a little bit dirty while building one of these. But this is going to be a really good intro to you. So lithium iodide aqueous is electrolyzed. When we have an electrolytic cell, a couple things we know. It is unfavorable. We have to make it happen. And in terms of a picture, the way that we can know that that will occur is instead of having a voltmeter, it has a power supply. It gets plugged into a battery, it gets plugged into the wall, or if we read the description of it, it might say that the reaction doesn't start until a voltage or power is supplied. So we've got lithium iodide. It's electrolyzed. I'm going to cover up the words aqueous for just a minute and then we'll come back to that. Let's pretend we just have lithium iodide. And since we are all chemistry experts, although that's a weird formula, I don't need an arrow, we're not in a reaction. That means maybe an equal sign would be better, is that it's lithium ion and that it's iodide ion. They're sticking together because I've got a positive charge and I've got a negative charge. So what I now do is I come down and I look, awesome. I have information that tells me about lithium ion and it tells me about iodide ion. So I can do this. On the other side, or when we were doing our galvanic cells, we were just trying to find the metals and rank them and figure out what was oxidized and reduced. And we're kind of using the same ideas here. The difference is that I don't use the reduction potential or the voltage to figure out what does what. I look at, well, what are the things I actually have? So with lithium iodide in electrolyzing it, I don't have solid lithium metal. I have lithium ion. And the only thing we can do with the lithium cation is exactly this. We can give the lithium cation an electron and turn it into lithium solid. So lithium ion cannot be reversed. Even though that reaction is a super, super, super negative. In fact, it's the most negative in the list that we will ever see. I can't make that go the other way because I don't have solid lithium metal. I have lithium ion. So that is how I figure out that if I just had lithium iodide, that lithium iodide has to be ugly handwriting, but it has to be my reduction. And that means my iodide right here, I don't have iodine solid. I don't have I2, I have I minus. So that is the one that has to be reversed. And when we think about this, this is the opposite of what we did before. It's like, wait a minute, why is the one that's negative staying negative? And why is the one that's positive becoming negative? Because I just said it's the opposite of what we did before. It is the opposite of what we did before. We aren't trying to make voltage, we are using voltage, or we are doing the thing that is the exact opposite of what would happen if we let it do it on its own. Electrolyzed means we're putting energy in and making this backwards thing happen. So if we did all of that, we could still get our overall potential. We would do 0.305 minus 0.53. We got a lot of threes and fives, and we would get 0.358, but it'd be super negative. We would need almost 4 volts, or else this stuff would just sit there and do nothing. And that doesn't seem too impossible or too hard. So we're like, okay, that's cool. I can put in 3 volts and make the lithium react. I can put in another half volt and make the iodide react. And what we would actually see was in that case is our cathode would get fatter. We would make solid lithium. That matches it up exactly with what we know and what we expect. Awesome. We would be making that. This one would be a little bit weird because before it was always kind of dissolving away, but this time we're turning a anion or a negative ion into this. So we would actually make some solid there as well. So the idea of something getting smaller and something getting bigger doesn't happen always, especially not in electrolytic cells, but the losing and gaining electrons, losing, gaining always happens. Electrons flowing from the anode, we're losing here, to the cathode, we're gaining, happens here. But in this case, we just have to look, what are the things that we actually have that we can actually react? So that's our scenario. We're good to go. We get 4 volts, we get some lithium iodide, and now we have some lithium and some iodine, and we're happy. But the problem is that we aren't happy yet because it says we are aqueous. There's reactions here that you are like, Mr. Morse, you're totally ignoring these two reactions, but that's cool because I don't want to look at them anyway. I have the two reactions that I need. So, yes, when I have lithium iodide, I only have lithium and I only have iodide. But when I have lithium iodide in my beaker, when it's aqueous, I have lithium ions. Cool. We said that. We get that. That's easy. I have iodide ions. Cool. We said that. That's easy. But aqueous means that there's not only those things, there is a lot of water molecules. So, yeah, I've got iodine there. Yeah, I've got lithium there. But I also have water in there. And why is that important? So, I'm going to, nope. Go back and for just a second, I'm going to erase that. We're going to think only about our reduction, only about our cathode. We think, okay, I've got lithium. If I want to turn to lithium ion into lithium solid, that would take 3 volts. No problem. Go get a couple batteries. That's 3 volts, and we can do that. But what else is hanging out here that can gain electrons? Oh, there isn't just lithium there. There's a whole bunch of water. And what happens is that lithium will gain an electron if I give it 3 volts, but the water will gain electrons with far less voltage. If there's only zero point 0.8 volts, or if there's less than a volt, that water can do a reduction. So at my cathode, although the lithium could gain an electron, the thing that really gains electrons are my waters. Boop. Super ugly. But what happens here is I am not choosing only the cation and only the anion at my cathode. Either my cation is reduced or I look, since there's a whole bunch of water, and if we are going to count molecules, like 90% of it or more is water. Well, what we're deciding is that cation going to be reduced or is the water going to be reduced? And we see, well, water is 3, almost 4 times easier to reduce than lithium. So at the cathode, water actually gets reduced. We're going to get a battery, we're going to stick it in some solutions, and we're going to see that sometimes the water reacts. And our evidence is going to be when water reacts, it turns into hydrogen gas and it can also turn into oxygen gas. So, what we can do is stick a battery into water. It seems weird, but it can start bubbling up and breaking down into the parts, into its hydrogen. So, for the cathode, we just decide, okay, the cation's super hard. Yeah, I could do that if that's the only thing that I had, but water's way easier. Awesome. That is going to be my reduction at the cathode. Well, what about the anode? We come back here. I erased it, but I have iodide minus. Awesome. I have lithium. Well, that was my thing. That's my cation. And I have water. So I have water and I have water. But when we're thinking about anode, we're thinking about oxidations. So we're thinking about reactions that go this way. So I am ignoring these bottom two because I already looked at and used those. Well, can I oxidize iodide? I can. I already talked about it before and said that it would take about a half of a volt, but I can also oxidize water. So what we're thinking about here is that same idea. I have an anion. Maybe that anion is oxidized, or maybe the water is oxidized. And when we look at this, we're like, awesome, water's super high, iodide's down lower. But we are reversing this. We don't want to think about these as reductions. These become oxidations. So if I wanted to make that go the other way, I would need to put in about a half of a volt to get my iodine to oxidize, but I would need to put in more than 1 volt to get my water to oxidize. So when we are looking at our anode, we are thinking, well, I've got an anion and that can be oxidized. I've got water and that can be oxidized. Which of those two is easier to oxidize? And in this case, because oxidation is the opposite, it's that guy right there. This is easier to oxidize my anion, or this, compared to that. That requires 1 volt or a half a volt. That's over a volt. So my cell potential overall, I have erased this guy, but I'm going to reduce my water. Boop. It takes 0.83 volts to do that. I'm going to oxidize my there we go. My iodine, that takes another half of a volt. If I can do math, and I don't totally trust myself, but I think I would come up with that answer right there. Nope, this should be a 6, I believe. So it's about 1.4 volts required, or I have to put that many volts in to make this happen. And if you go back to the beginning of the video, you're like, cool, that takes some voltage. But if we did it any other way, if we just had lithium and we just had iodide, that took almost full 4 volts. This takes less than 1.5 volts. So that's why it happens. When we are in aqueous solution, we are thinking about for the cathode. We compare our cation, and I'm going to clear this off, for the in aqueous, we think, is it easier to reduce my cation or my water? Well, which one has a voltage that's closer to being positive? And then at my anode, which one's easier to reduce, my anion or water? Which one has a reduction potential? Well, not a big reduction, because we want a oxidation potential. So we've got that right there. So right here, it kind of shows what would be going on, but we can draw, okay, electrons are flowing this way from anode. So over here, we would see one thing. We would see our oxidation that we just wrote. Over here is my cathode, and we would see that as well. Down here, this just becomes a stoichiometry or a dimensional analysis problem. An amp is a coulomb per second. So I can't write this all out without it looking super, super ugly. But what you end up doing on this is thinking about, okay, if it's that many coulombs per second, how many seconds is 45 minutes? Okay, it's been going that long. Well, how many coulombs is that? It's going to give you a whole bunch of coulombs. And then we think, well, I don't know what a coulomb is. And good news, you don't need to care what a coulomb is. But Faraday's constant told us that there's 96,485 coulombs in every mole of electrons. So we make that connection, and then we just continue on, because now we are in the part of stoichiometry that we like and that makes sense. We are thinking about moles and we are thinking about electrons. So for both of these, pull up the answer key and kind of think about it, but it's just based upon that flow of electrons. I wanted to take the time to go through this, to talk a little bit too long, so that you could see it and start to have some hope as to what you saw and what to think about on the lab. I'm going to make a video. I'm sure it won't be quick. I'll try to make it quick, about help with the lab. But this gives you just enough to kind of get started thinking about the other version of electrochemical cells.